Okay, here's lesson 3. We are going to learn, or we're going to define function as a relation that assigns each element of the domain to exactly one element of a range. We're going to be writing equations using function notation. We are going to represent multiple representations of functions. We are going to determine and recognize if it is a function, and we are going to group function families. We have a whole bunch of key terms that are all over here in your glossary. Relations are not necessarily functions. Relations are just two measurements that are being compared together, perhaps in graph form, perhaps in table form. A couple of things. We know that domain is the X. We know that range is the Y. A function we're going to get into in a minute. We're going to review that concept, and we're going to review function notation. The vertical line test is where I drew that vertical line. And remember, we moved it from left to right across the picture to see if we touch the picture in 2 points, or in 2 places. If we do, it fails, and we'll see that. Discrete would be if I have a graph that's got dots and they are not connected. Continuous may have dots, may not have dots, but they are, these points are connected by a line. An increasing function is going up. It could be a straight line or it could be a curved line. A decreasing function is going down. Could be straight, could be a curve, it could be any formation. Constant would be when you have a function that's going straight across, it's flat. Function families. We've learned about linear functions. This is called a quadratic, an exponential, and we're also going to learn about quadratic functions. And this is them being broken down linear, and we're going to see linear, exponential, quadratic, okay? Absolute minimum is when you have a quadratic and it's got a bottom point. Absolute maximum is when you have a quadratic and it has a top point. X-intercept, when you're looking at a graph. Remember, you have your x-axis and your y-axis. If I draw a line on these axes, okay, your x-intercept is right here where it touches the x-axis. Your y-intercept is right here where it touches the y-axis, okay? So that's just a preview of some vocabulary terms. We're going to go ahead and jump on in. Odd man out. So if I have a student and we are looking at these pictures, which one of these is the odd man out? What's different? Okay, I had some kids say some different stuff. I had one student say that D was the odd man out because it was only in 2 quadrants. And I said, okay, great. So everybody else is in how many? Well, if you look at graph A, it is in, I'm going to get my little pointer going here. I pressed the wrong thing. Sorry, y'all. Okay, this one's in 1, 2, 3 quadrants. Graph B is in 1, 2, 3 quadrants, but graph C is in 4 quadrants. So technically, graph D is not the odd man out because of that, because A and B are one way, C is one way, D is one way. So I wouldn't say that's a great explanation, but here is one that you may remember that you should have seen in 8th grade, and if you haven't, I'm going to show it to you now. This is the vertical line test. I mentioned it in the last lesson, okay? So what I'm going to do is I'm going to take my vertical line, and I'm going to move it across the picture. And if you'll look, never at any time is my vertical line touching in more than one spot on the graph as I go from left to right. When I get to graph B, it is also not touching in more than one spot. When I get to graph C, it's not touching more than one spot. But when you get to graph D, covers up the whole thing, okay? Graph D fails the vertical line test. This is a function test. It fails the vertical line test. And so it is not a function. So we're going to talk about how do you know if we have a function or not a function. Well, here's my first one. I have all these 6 different ways to represent relationships. I've got ordered pairs, an equation, a verbal description, something called mapping that you should have seen last year, a graph, and a table. It all comes down to this. Don't go back to your X's, okay? Once you're done with an X, don't go back to it. Do that in relationships too. Don't go back to your X's. Don't repeat your X's. okay? When you're looking at ordered pairs, X, Y, I am just going to go through and look at my X's. -2, 0, 3, 3. Uh-oh, I have repeated my X's. This is not a function because it repeated the X's, okay? If I have an equation, I'm going to go graph it. Now, there's two ways you could do. You could graph it or you could make a table. I'm going to go graph it because you guys will have the ability to use this cool thing called Desmos that we've been talking about. I can go out to Desmos and I can type in there y equals 2/3 x minus 1. And as soon as I graph that, I can see that it is a straight line. And if I wanted to, I could even press that little gear button up there and press a table. And as you can see, none of my X's are getting repeated. And if you were to do the vertical line test across this picture, it is not going to repeat. So this one is a function, okay? It's a relationship, but I'm representing a function. So this one is a function, okay? I'll go back over to the big picture again. We'll go back to full screen. Okay. Verbal, the relationship between students in your school and each student's birthday. If I was to make a table and I had students' names and I had their birthdays, and I had a student named Joe, and maybe Joe was February 21st, and then I had Martin, and his is January the 4th. And then I had Lucy, and her birthday was, September the 4th, okay? And then I have Gloria, and Gloria was 1/4. Well, notice that Gloria and Martine have the same birthday, but they have different names. Each individual person, this is kind of like your X column. Each person is like being an X, and I am not repeating my X's. I have an individual kid. Each individual kid only has one birthday. So each individual kid does not have two different birthdays. So I'm talking about a relationship between the name of the person and the birthday. I'm going to have no repeats. Okay, this is mapping. And I'm sorry, this one is a function. Because the big idea with this lesson is it a function or not? This one is. Okay, mapping. The way I look at mapping, because it used to confuse me, is I'm going to look at each individual line. Each individual line is like an ordered pair. It represents an ordered pair. So I have the point 1, 2, okay? My next line, I'm connecting 4, 5. My next line, I'm connecting 4, -5. My next line, I'm connecting 2, 0. Now, I want you to look at all of those. Remember I said don't repeat your X's? And it looks like, and I shouldn't have highlighted all of that, it looks like I did repeat my X's. The number 4, when it was put in, that was my input because the left side is my X or my input and the right side is my Y or my output. If any of my X's got repeated, then it is not a function. Not a function. Remember, X is the domain, Y is the range. Okay. Got a graph. If you have a graph, you can check to see if it's a function by doing our good old vertical line test. So we're going to do that. I'll make my vertical line. It's a good thing this software straightens that line for me. I'm going to move my vertical line, and I'm only touching one X at a time. And I want you to understand what this means right here, okay? When you're only touching one X at a time, it means wherever I stop, okay, this looks like this is the point 4, 2. Nowhere else on this graph am I ever touching 4, and I'm only touching 4 one time. When I move the line, I'm moving on to other X values. So I am never repeating and seeing the same number. Now I'm going to draw something that's not a function on this graph. Let's say that I'm going to do it in black. Go back. I'm going to draw a different picture. Let's say that I drew this picture. Okay, and I'm going to do the same vertical line test. When I move my little vertical line over here, I'll move it right here. You can see that I have a point here and a point here. They have the same x. These are both on 8. X is 8. And y, it looks like is -6 on the top one. And it looks like it's pretty close to -10 on the bottom one. That is not allowed. You cannot have the same x and have it spit out different y values. So that second picture that I drew, this would not be a function. But the picture that was already on the graph was a function, okay? So this is a function. This is a relation that is a function. Last one, domain, range. Do you have any x's that repeat? I got a 1, a 2, a 5, a 6, a 7. I don't even care about the y column. Don't even look at it. No repeats in the x column. So no x repeats. This is a function. So this is the kind of stuff you're going to be looking for, guys. Is it a function or not a function? Okay. When you have a function, functions can be written in something called function notation. And they're going to start with f of x. It could be f of x. It could be g of x. I could call it something like c of s. All the function notation is telling you is it's saying this is the name of the function. This particular function is called f of x. And it's telling you everywhere you see an x, if you want to know what a particular output is, just tell me what x you want to put in the table. So function of 2 would be 8 times 2 plus 15. That's the way a function works. It's basically a rule, and it's telling you, hey, if you'll give me an input, an x, I can tell you what the output is. So in the case that I have over here, 16 plus 15 is 31. When the input is 2, the output is 31. So I could graph this function, and I guarantee you that the point 2, 31, is on the graph. And in fact, I'm going to show you guys, anytime you have a function like this, you can actually graph it in Desmos, and you can see what it's going to look like. So I'm going to go graph f of x equals, what was it, 8x plus 15? 8x plus 15. There's my graph. I'm going to go click on this table over here. And like I said, y'all see this 2 down here? When x is 2, y, it's way up here at the top. I can click on it. Y is going to be 31. So I could have done it by hand and figured out what some points were on this function, but I can also go graph it in Desmos. To graph it in Desmos, you got to use x's and y's, or f of x and x. Just letting you know, I could write this exact same function using the name c, and I could say I'm inputting an s. C is still the output, S is still the input. So whatever your function name is, that is your output. Whatever is in the parentheses, that is your domain or your input, okay? So like I said, this is your domain, or in other words, your input. This is your range or output. Okay. All righty. When you have a function, once you know what the function is, you should be able to identify your x and y values. I'm going to go back to my Desmos for just a second. In this particular, sorry about that. In this particular function that I just did, I'm going to do it again. F of x equals 8x plus 15. And I did a little table over here. Okay. My domain would be all of these x values. So -2, -1, 0, 1, 2. And I could keep going with that. I could keep adding domains. The range is going to be over here on the right side. All of your output values. So you've got a domain and you've got a range. Okay, so they're giving you a worked example in your textbook. This is on page 42. The domain, these are all of your x values. The range is all of your y values. And here is the scenario that this came from. You have a teacher and she's going to have students for tutoring. She's going to have no more than 6 kids. Well, how many kids can that be? You can't have 2.5 kids, but you could have 0 kids, 1 kid, 2 kid, 3 kid, 4 kid, 5 kid, 6 kid. Based on the number of kids she has, she's going to have supplies for those kids. And she is going to give 12 pencils to each kid. She doesn't know how many pencils she gives out until the kids show up. That's why this is your independent variable and this is your dependent variable, because kids determines how many pencils she needs to give out. If nobody shows up, she's not handing out any pencils. If 1 kid shows up, she's giving out 12. 2 kids, she's going to need 12 for both of them. That's 12 plus 12 or 24. 36, 48, 60, 72. So it skip counts by 12. She knows she's going to need somewhere between 0 and 72 pencils. Okay? So the domain is the number of kids. The range is the number of pencils. I have here a bakery scenario. We're going to sell bagels in sets of 6. We're only going to sell to the first 9 customers. Well, guys, the domain's going to be the customers. How many customers I have is going to determine how many bagels I sell. So I can either have, and we put this in called a set. I can either have 0 customers, 1 customer, 2 customer, 3, 4, 5, 6, 7, 8, or 9. That's all. I'm not selling any more bagels after customer number 9. Now, if no customers come, I guess I'm not selling any bagels. But if 1 customer comes and I'm selling them in a set of 6, I'm selling 6 bagels. 2 customers, 12 bagels. 3 customers, 18, and so forth. I'm skip counting. Does everybody see how I'm skip counting by 6s there? And it's going to go all the way up to, let's see, 9 times 6, all the way up to 54 bagels. So the number of bagels that I sell depends on how many customers show up. Okay? Letter B. This is a graph. If I ask you for the domain and range of a graph, super easy. Your domain, remember, is your x values. So here's my x values. 0, 1, 2, 3, and 4. My x values are these exact numbers, 0, 1, 2, 3, and 4. My y values, based on the graph, you got this one at 5, 10, 15, 20, and 25. So here are my y values, my range. So this is domain. Here is my range. I'm going to put this up here with the y from the y-axis. 5, 10, 15, 20, 25. Now, guys, this is the ordered pair 0, 5. So do you see how the 0 went with the domain and the 5 went with the range? The next point, I'm going to do it in black, is 1, 10. And then we had 2, 15, 3, 20, and 4, 25. So you can see all those numbers and where they went. The first number is the X. It goes with domain. The second number is the Y. It goes with range. All right. Vertical line test I've already talked about with you. And again, I know you saw it last year. So since we've already seen it, just running through it real quick. This one passes the vertical line test. It always touches in one spot. The second one is not a function because it does not pass the vertical line test. You have the same x value as two y values when you're looking at it on a graph. Okay. Let's talk about discrete and continuous. Discrete and continuous. This was a discrete graph. Discrete is where you have individual points not connected with a line. Continuous is these two graphs. They are a complete, it's a connected line. So there's no break in the line. That's how you know the difference between discrete and continuous. Now, when do you use which? Discrete is actually both of these examples that they gave you up here. The teacher with the pencil, it doesn't make sense to draw a graph of the teacher and the pencils and say one student gets 12 pencils, 0 students gets 0 pencils, and connect that line. Because what values are between 0 and 1? You can't have 0.5 students getting 6 pencils. We don't count the kids by decimals. So the domain, since it has to be whole numbers, that means your range also has to be a whole number. The same thing with the bakery scenario. If I'm selling bagels in sets of 6 and it's based on my customers, I'm never going to sell 3 bagels, okay? I'm going to sell 6 bagels to the first customer, and then I'm going to be up to 12 after I get to 2 customers. You're not going to have 1.5 customers. This is a discrete graph situation. That's when you use discrete. Continuous might be something like temperature. If you were graphing the cooling time, and because we had one of these in a prior lesson, and something started off at say 100 degrees, and you removed it from the heat. Over time, time does not jump. You don't jump from 0 minutes to 1 minute. You go by seconds constantly to the first minute. And we know that over time, the temperature is going to drop. The temperature does not drop from 100 to 75. It doesn't do that. It gradually drops to 99, 98, 97. Now, it might drop quickly, but it does not skip from 100 to 75 degrees. So time and temperature are going to be continuous measures. Okay. We're going to determine if each one of these represents a function. Since a couple of these are graphs, I'm going to pull up Desmos. I don't need for you to guess, graph it. So I'm going to type in y equals 3 to the x power. Look at that. I can see the graph. And if you were to do a vertical line test, because it looks something like this, I'm going to go sketch it on my paper. It looks something like this. But if I was to go do a vertical line test, because that's what I do when I have graphs, it is going to, oh, hello, I didn't want to move the whole thing. It is going to pass the vertical line test. It's never going to touch in 2 places, okay? For every house, there is only one street address. That is a function. So this relation is a yes. This one is also a yes. If you're going to send mail to my house, I have an address. It has a number, it has a street name, city, state, zip. When you put that letter in the mail, it's only going to come to me. It's not going to go to somebody else who has the same street number and name. It's going to come to me because you have a complete address. So each house is the input, and each house does, in fact, have a different street address. That's a function. Letter C, not a function because your x's repeated, not a function. Letter D, let's look at our mapping. Remember, we were going to look at each line. So 2, unfortunately, goes to 7. Oops, let's use the pen. 2 goes to 7, but it also goes to 20. That's not allowed. Your x's cannot repeat. So because 2 got repeated, it is not a function. Okay, this next one, I got a -7, a -5, a 2, and a 3. Notice I didn't even look at the y's. I don't care. X's did not repeat. This is a function. Okay, last one, I'm going to do a vertical line test. Oh, I'll just draw another vertical line. And let's go move it. And it passes. The whole way across, it passes. It never touches twice. So this one is a function. Okay? All right, that's the big idea behind this lesson. We're going to move on to an activity, and we're going to talk about something called domain and range a little bit more specifically. All right, when you've got domain and range, again, domain is all of your x values, okay? And whether it's verbally or in a graph, it's the x values. So these are worked examples. There are a couple of typos, and I'm going to fix these real quick. I know this is supposed to be a y, so I'm going to go ahead and fix it. I know this is supposed to be a 9. I think that's it. I think the rest of it's right. Okay, so I'm going to show you domain and range. So if I want to do domain of the first graph, first of all, you are only allowed to look at the x-axis. And I'm going to use a vertical line to demonstrate domain. Okay, you're looking at the x-axis, and you only get your numbers off the x-axis. I'm going to use this, and you could use your pencil, and I'm going to start on the left side of the graph. And I am looking for, where does the picture that's drawn on the graph first line up with the x-axis? And as you can see, I have stopped. It looks like x is -2. -2 is the smallest x there is on my graph. And I'm going to write that down. -2. And it's the smallest x. Now I'm going to move this thing again. And this time I'm going to go over to the right side. I want to know what's the furthest to the right I have any numbers. And I move it over this way, and it looks like it's at around positive, oh, I can't really tell. I got to zoom in a little bit. +5, okay? So where that black dot on the widest part of my graph, the furthest to the right, it is at +5. So all of my x's are between -2 and 5. But here's the deal. One of these has an open circle, and one of these has a closed circle. That open circle where the -2 means that this graph gets right up to the -2, but it never actually touches the -2. So I'm simply going to say less than in my statement. But on the right side, my graph not only comes right up to the 5, it actually is on the 5 with a solid dot. You're going to use the less than or equal to symbol. So if I was going to say, what is the domain of the first graph? I'm going to say x is greater than -2, but it's less than or equal to 5. And that's what this looks like here and here. Okay? Now I'm going to go look at the domain of the second graph. We're going to do the same thing. I'm going to highlight the line. You're only allowed to look at the numbers on the highlighted line. I'm going to go take my little vertical line that I used on the previous example, and I'm going to come over here and I'm going to say, okay, where do I first touch the graph? Well, this time it's touching at an arrow. It's not a point at all. So where does x start? Well, if it's an arrow, that means it's going to keep going to the left to in negative infinity. It's never going to stop. I don't know where this graph starts because it's an arrow. It keeps going. The same thing is going to happen on the right side. If I come to the right side and I scooch over, look, it's stopping at that arrow. That is positive infinity. So there really is no boundary for my x's. It could be as small as negative infinity or as big as positive infinity. We call that all real numbers. And the way you write it is you put the x in between the infinity symbols, okay? So that's domain. Now, I'm going to change colors on us. In fact, I'm going to take off the green altogether, or the green highlighter. I'm going to take it off. Let me go hit my eraser, and let's erase this, and we're going to erase this, okay? So that's all erased. So now I need you to focus your attention on the y-axis. We're going to talk about range. This time you can only get your numbers from the y-axis. So I'm going to take this lovely little line over here, and I'm going to get rid of it. Let's say I'm going to get rid of it. I'm going to draw another one. This time I'm going to draw a horizontal line. Okay? And we are going to look from the bottom of this graph up to the top. Bottom, top. What's the lowest y value that you see on your graph? Well, if you look at what that's in line with, it looks like it's at -7. And the highest y value I see on my graph is all the way up here at 9. So all of my y's are in between this -7 and this 9, okay? So I'm going to do this, and then I'm going to go look at the dots. The dot in line with the -7 is solid, so I'm going to put a line under. That means y is greater than or equal to -7 or equal to, okay? The dot at the top is also solid, so it's going to have a greater than or equal to. So, oh, this one did have mistakes. So this is supposed to say -7 and +9. So the range is all the numbers that are greater than or equal to -7, less than or equal to 9. That is the range of the first graph. Now we're going to go look at the second graph. And I'm going to take this guy off of here, I think. Or turn it. We'll turn it. There you go. That'll work. Okay. We're going to do the same thing we did with domain, but we're only going to look up and down, okay? I'm going to make this a little bit longer and straighter. Okay, so I'm going to start from the bottom. Ooh, what's the first thing I touch? Arrows. Arrows mean infinity. Since this one's the bottom, it's -infinity. So -infinity. Now I'm going to go see where the top is. The top looks like it's up here at 9. So all of my y's are between -infinity and 9. Now, there's no arrows, so we're just going to say y is bigger than -infinity. There is a dot at the top that's solid, so y is less than or equal to 9. Guys, since there's really no boundary on the left-hand side, it goes to infinity, but there is a boundary on the right side, we're just going to look at the right side. Y is less than or equal to 9. That is my range. So this is how we do domain and range, and we're going to do some more of these, okay? We've already talked about these properties, so I'm just going to sketch a graph. Increasing looks like this. Could be exponential, could be linear. Decreasing looks like this. Could be exponential, could be linear. Constant is flat. That's where your graph is neither going up or down. Combination is when you have a quadratic. This quadratic first goes up, it's going up, it gets to a midpoint, and then it starts going down. Or it could be one that starts out going down and then turns around and goes up. Now, we're going to look at these different types of functions. You've already seen them in graph form, but if on a test or in another situation, if we give you the equation, I don't need for you to guess what that looks like. Just go graph it, okay? So I'm in Desmos right now, and I'm going to graph some of these. F of x equals x. Oops, I forgot the equal sign. Equals x. So y'all can see that's a straight line. So that is a linear increasing function. Oops. And we're going to go pick these. There's some graphs on a subsequent page. It looks like this. So if I go down to the next, gosh, there's a page somewhere on here that's got some of these on it. Yeah. And so, you know what, we're just going to sketch it on there. We're not going to try to match it. We're just going to sketch it. These are some of the graphs that we cut out at one point. So we're just going to draw it like that, okay? My next graph, And by the way, this is called linear. Okay, the next one says 1/2 to the x. So I'm going to go type in parentheses 1 divided by 2. That's how you do 1/2. You do have to arrow out from under the fraction bar, and then you hit the A to the B button to get an x up there. So that is an exponential function. It's decreasing. Okay. Same function, but this time I'm going to put a -5. So you can see it is also decreasing. But notice this one dropped down, okay? When there was no -5, if you look up here where the y-intercept was, it was up at 0, 1. But when I put the -5, look where my y-intercept drops down to. Drops down to 0, -4. So it's just lower, okay? F of x equals 2. That's going to be a straight line, and it's going to be a constant, okay? F of x equals 2 to the x. That one's going to be exponential. So exponential, this one's linear, exponential, okay? And then negative x plus 3. Okay? And that one is just going to be linear. Now, I want you to notice something about these, okay? The ones that were exponential, I want you to notice that all of them have an exponent, and it's an x. Anytime x is your exponent, you get an exponential function. Now, we're also going to see later on that when a 2 is your exponent, we're going to get a quadratic function, okay? Let's see. So let's go back and look at the linear functions. Notice the linear functions, no exponent, okay? So on the linear functions, f of x equals x, no exponent. F of x equals 2, no exponent. F of x equals negative x plus 3, no exponent. So when we're linear, no exponent, okay? So I'm just going to make a note of that in your book. No exponent. That's kind of how you can tell. But again, you don't have to guess, because you can always just go type it into Desmos. Linear is going to have no exponent. Quadratic, we haven't seen yet. So let's go take a look at these. Quadratic, I'm going to graph this one. This one looks a little different. I see an exponent, but it's not an x. The exponent is a 2. And that's what I was just talking about. So you see how I have a quadratic? Okay, there's a quadratic. Now, I do want to talk about a couple of new terms, absolute minimum or maximum. Absolute minimum is when you have a bottom. If you can see the bottom, it is a minimum. Guys, you can't see the top. I know you might think you can see the top, but you can't, because arrows means it goes up forever. So you have no way, come over here and look at my Desmos screen. You can see that that bottom point is -4 and -4, but you have no idea what the top of the graph is because it goes right off the page. So I can't see the top, so you can't tell me what the absolute maximum number is. But I can see the bottom, and I can see that my absolute minimum is -4, the y value, okay? Now I'm going to type the next one in. I've got -3x squared plus 4. Oops, that did not work. Equals -3x squared plus 4. Okay? This one, if you look over at my graph, this one, look how it looks. Okay? But this time I can see the top. It's at 0, 4. This one, if I can see the top, then the maximum height this graph goes, the highest it goes, is y equals 4, or to the point 0, 4. I can see the top. So this one has an absolute maximum. Okay, the last one is just f of x equals x squared. Notice this one is straight up and down, so I can see the bottom. I can click on it, y equals 0, or in other words, 0, 0. This one has an absolute minimum. I want you guys to notice something about these, okay? The two that have bottoms, they're pointing up. Notice that both of the X's are positives. The guy that's pointing down, notice there's a negative in front of it. That's why it's upside down or flipped upside down, okay? So quadratic functions, you're going to know them because they're going to have the minimum or the maximum, this U shape, and your exponent is a 2, okay? So function families, I'm just going to move on through this. Function families, you know, you're looking at linear could increase or decrease. Exponential can increase or decrease. And your quadratics are going to do both. Okay, they're going to increase and decrease. I'm not going to go through this graphic organizer. You guys can kind of see it. So the big idea is linear, it's straight and it's either up or it's going down. Okay. Quadratic, it's curved and it's either going up or it's going down. Quadratic is curved. It's doing both. It either starts out going up and then coming down, or it starts out going down and then going up. And quadratics have an absolute minimum or maximum. And that is it for lesson 3.